Hello friends, today we are going to see the binary search algorithm to search an element in an array. So let's see what it is. So this is an array and suppose for example we want to find out element 30 in the array. We want to search element 30 in this array. So here the search element is 30. Okay. So now you will go on searching one by one and you will access each memory location of the array and you will check whether that element is 30 or not. And when you will come at the 7th index, then you will see there is 30 and 30 will match to your search element, that is 30, and you will return index 7 as the index of the search element inside this array. So now this method of searching every memory location in this array in a sequence is called as linear search. So in linear search, if your element lies at the 7th index, then you access total 8 memory locations, that is 0 to 7 means 8 memory locations. In the worst case, if your element lies at the 9th memory location in this array, then you will go from 0 to 9 means you will access 10 memory locations. You will access 10 memory locations means in the worst case the linear search time complexity is O of n. N is the number of elements in the array. Now suppose you want to find out or you want to search 34 in the array. Okay, so we will see another efficient search algorithm to find out 34. So the other algorithm is binary search algorithm, and these are the steps to follow for binary search algorithm. So here the first step is find middle index of the array. So this is the array and you are going to find out the middle index. So how to find it out? See, your range is 0 to n minus 1. If there are n elements in the array, then 0 to n minus 1 is your range. So the middle element m is equal to s plus e by 2. So what is s and what is e? S is the starting index and e is the ending index. Okay. Now s plus e by 2. So 0 plus 9 by 2 means here it is 9 by 2. So 9 by 2 is 4. The integer answer is 4. So the value of m here is 4. Okay, and as you know s is equal to 0 and e is equal to 9. Okay, and the middle element index is 4. So now let's check the next step. So it is check if search element equal to array of m. That means you have to see whether the search element 34 is equal to the middle index element or not. The middle index is 4, so the element is 12. 12 is not equal to 34. So if it is not equal, then you have to make two parts of the array. Means you have to divide the array. Remember that this is a sorted array in ascending order. Sorted array. And it is ascending order. So now as 12 is not equal to 34, now you have to follow the process to divide. So the part 1 and part 2 are the two parts we get after dividing the array. So part 1 is s to m minus 1. So that is the index. See here. So s is 0. So s equal to 0 to m minus 1. So what is m minus 1? As m is 4, m minus 1 is 3. So for this part, s is 0 and e is 3. See, this is that part. I will give the index 0, 1, 2 and 3. So for this part, the starting index is 0 and the ending index is 3. S equal to 0 to 3. And let's see the next part. The second part is m plus 1 to e. So this is the second part. M is 4, so m plus 1 is 5. So s equal to 5 to what is the last index, that is 9. So m plus 1 to e. E is 9. So these are the two parts, 0 to 3 and 5 to 9. So now let's give the indices here, 5, 6, 7, 8 and 9. Okay, now let's go to the third step. So the third step is decide. Now what to decide? See, which part may contain the search element? You have to decide that. So how do you decide? So it is a part of common sense that if it is a sorted array and if the given array is sorted in ascending order, then your search element 34, if it is greater than the middle element, that is 12, then obviously it should be present, that is 34 should be present ahead of 12 in this array, in the next part of the array, means after 12. Okay, because 34 is greater than 12 and this is a sorted array in ascending order, so 34 should be after 12. Okay, so that is written here. If search element is less than array of m, so if your search element is less than 12, less than the middle element, then it should lie before 12. That is written here. If search element is less than array of m, it should lie in part 1, that is the left part. And if search element is greater than the array element, that is the middle element, then it should lie in part 2, that is the right part, which is the case here. 34 is greater than 12, so it should lie in the right part, that is the part second. Okay, so this is the part in which 34 is present. Now we have to concentrate on this part. Now this is our array and we are sure that if 34 is present inside this array, then it should be present inside this part of the array. Okay, so now we take this part and we perform the same procedure again on this part of the array. We consider this as the parameter for this iteration of this loop. These three steps are going to be executed inside a loop. So now see, range is from 5 to 9 here, 5 to 9. Okay, so m equal to s plus e by 2. S is 5, e is 9. Okay, so 9 plus 5 is 14. So 5 plus 9 by 2. So that is 14 by 2. So that is 7. Means now the middle element is 7. Okay, as the middle element is 7, now you have to check the middle index element with the search element like mentioned here. See whether 34 is equal to the middle element, that is 30 here. Are they equal? No, they are not equal. So if they are not equal, make two parts of the array. So we have to make two parts of this array now, or this part of the whole array. So now it is, the part 1 is s to m minus 1 and m plus 1 to e. So see here, we have to make two parts. s equal to 5 to m minus 1, so that is 7 minus 1, so that is 6. S equal to 5 and E equal to 6 for this part of the array. This is the first part, okay, and this is the second part, that is m plus 1 to E, means m plus 1 means 7 plus 1, because m is 7, so 7 plus 1 is 8, 8 to E is 9, okay, E is 9 for this range, so E equal to 9, okay. See, 0 to 9 divided into 0 to 3 and 5 to 9, 5 to 9 divided into 5 to 6 to 8 to 9. Now what is the third step? Decide which part may contain the search element, okay. As you know, you have to compare the search element with that middle element and then decide. So as 34 is greater than the middle element 30, 34 should lie in the right part, that is the part next to the middle element, so that will lie inside the second part, this part. So in this part the indexes are 8 and 9, 8 and 9. So S is 8 and E is 9, okay. So the range is 8 to 9, okay. So as you can see, we are iterating in the loop. So again in the next iteration, range is 8 to 9, so find out m now, S plus E by 2. 9 plus 8 is 17. See here, 8 plus 9 is 17 by 2. 17 by 2 is 8. So m is 8 now. M is 8. So as m is 8, so you have to check whether search element 34 is equal to array of 8, that is the middle element. What is array of 8? It is 34. So yes, 34 is equal to 34. So we have found out that element inside this array. So we will return the index of that element, that is m. M is the index of that element, okay, and we will stop here. So this is how we search an element inside the array using binary search. Now what is the time complexity for this? What is the time complexity? See here, this structure of divide and conquer is same as a binary tree, okay. So if you have 10 elements in the array, then the height of this binary tree will be equal to log n. Log to the base 2 will be equal to log n. So as the number of elements in this array are 10, so log n must be 3 point something, okay. So this means you have to access 3 memory locations to search 34. In linear search, you had to search for 9 memory locations to find out 34. But by using binary search, we found out 34 only in 3 memory location accesses. So now suppose you want to search 7, okay, you want to search 7. So let's repeat the process. So see here, 12 was the middle element at first. So as 7, our search element is 7 now. As 7 is less than 12, 7 should lie in the first part, in the left part, okay. So you go inside this left part. So inside this part, now you have to check the middle element, that is 0 plus 3 by 2. 0 plus 3 by 2. So 0 plus 3 by 2 is 1. So m is 1 for this, okay. M is 1. So this is the middle element. Check whether 7 is equal to 5. No. So now as 7 is greater than 5, that will lie inside the second part of this division. So this division will be this 2 and 7 11. Okay, so see how will be the division. As m is equal to 1, the division is s to m minus 1 and m plus 1 to e. So here s is 0. See here s is 0 and e is 3. So s is 0 to m minus 1. M is 1. So 1 minus 1 is 0. So 0 to 0, which is why this only one element comes in this part, and m plus 1 to e. So as m is 1, so m plus 1 is 2 to e is 3. So 2 to 3. So this is the another division. Okay, so now you have to check whether the search element 7 is greater than or less than 5. As it is greater than 5, it will be in this part. So now 2 plus 3 is 5. 5 by 2 is 2. So 2 is the middle element. M is equal to 2. So as m is equal to 2, check whether search element 7 is equal to array of 2. Yes, it is. It is equal. So we return. So we return m, that is 2. That is the index of the element which we are searching for. So that index is 2 and the element is 7. So now see how many memory accesses we did. We did 3 memory accesses. First for 12, then 5, and then for 7. 3 memory accesses. But if we go for linear search to search 7, then also we go with only 3 memory accesses. So you may say that then this algorithm performs in the same way for linear search and binary search if the element is in the first part of the array, if it is in the first half. Okay, but this is not true, because here are very less elements. There are only 10 elements. So log n is about 3 point something, that is 3 to 4. So 3 to 4 memory accesses. But suppose if there are, here I will write 512 elements inside an array. Okay, if there are 512 elements, then if your element is at 250th location, okay, if your element is at 250th location, so here if there are 512 elements and if your element has 250th location, then you need log 512 memory accesses, that is to the base 2. That means you need about 9 memory accesses. See, you need about 9 memory accesses, and if the element is present in the second half, then also you need 9 memory accesses. So whatever is it is in the first half or second half, you need 9 memory accesses for 512 elements. So when there are many elements in the array, then binary search performs very efficiently than linear search. So this is the advantage of binary search, but the only thing is that your array should be sorted. So binary search performs better when there are many search queries for the array. So suppose if you have only one search query, for that one search query you have to sort the whole array, and the sorting time complexity is n log n, sorting. So only for one search query this n log n time complexity is not affordable. So you can sort the array only if you have many search queries for that array. That time it works efficiently. Hey friends, please subscribe to my channel as I post algorithm videos every day. And if you want a video on any particular topic, then please mention in the comment below. Thank you.